Hi, Algebra 2 students. These notes are on solving exponential and logarithmic equations, and we started doing this a little bit in class, so I'm just going to formalize it and show you guys some examples. But before we get into the examples, I just want us to recall the first way that we learned how to solve exponential equations was to solve by equating the exponents. And what I mean by that, if I just do a quick example, would be something like 4 to the x is equal to 2 to the x minus 3. Well, then we could rewrite 4 to the x as 2 squared to the x is equal to 2 to the x minus 3. And now I can set the exponents equal because I have the same base. So we would get 2x is equal to x minus 3. From there we can subtract x and we get x is equal to negative 3. Now the problem with this method is that it won't always be possible. So this doesn't always work. And just to kind of clarify why it doesn't always work is if I just switched out that 4 for a 5 in the equation, then I have 5 to the x is equal to 2 to the x minus 3. I can't think of any way to rewrite 5 so that it's some power of 2, right? So this is a situation where we would need to do something different. Okay, so now I'm going to kind of introduce some properties that we're going to be using while we solve these equations. So we have certain properties of equality. So the properties of equality are going to be the idea that if we have b to the y is equal to b to the x, then if this is true, then it also must be true that y equals x. So this is the idea that we can equate the exponents of y and x if we have the same basis. That's what we used up here. And we have something similar with logarithms. We'd say log base b of y. If you know log base b of y equals log base b of x, then it's also true that y must equal x. And so the idea of these double-sided arrows is if you know one, you can get to the other. If you know the other, you can get to the first. So it kind of works both ways. Okay, and the other properties I want us to write down are some logarithm properties we're going to be using today when we're solving. And the first one is one we've looked at before, which is log base b of b to the x. This will always equal x. So we started seeing this again in action today and how this can help us with the idea that we know that log base b of b is just 1, and we know our exponent can scoot out front. Therefore, this would become like x times 1, which is just x. Okay? So that should make some good sense as to why log base b of b to the x is x. The second one might hurt your brain a little bit to think about, but it's a similar idea. So if we have b raised to the log base b of x power. So that is, again, this is kind of complex to think about, but I want to remind you that log base b of x means b to what power is x. So like this is the value of log base b of x is the exponent that when we raise it to the b power, so b raised to this power, it will always equal x. So that means b raised to the log base b power of x will always just equal x. So what we're kind of seeing here is this idea that if I take a log of an exponent where the bases match, the base and the log cancel, and I'm left with my exponent. And similarly here, the base and the log will cancel, and we're kind of left with that x. And this is how we're going to be solving logarithmic and exponential equations. So for my first example, we have 4 to the x is equal to 11. So I would like to get this x out of the exponent. So the idea is that I would have to take this and raise it to the power, or sorry, take the log of this, but I need my base here to match the base I see with my exponent. So I would do log base 4 of 4 to the x. And on the other side, I need to do the same thing. So it would be log base 4 of 11. So on the left-hand side, I know that log base 4 of 4 to the x is just x. And on the right-hand side, I'm just going to write this as log 4 of 11. Now, I don't actually know what the value of log 4 of 11 is, log base 4 of 11, but I could then rely on my calculator. So I could do the change of base formula, which would be log of 11 over log of 4. And then if you type this into your calculator, you'll get an approximate answer of 1.73 for x. So our next example is log base 5 of 4x minus 7 is equal to log base 5 of x plus 5. So now if you take a look, I see I have logarithms on both sides and I have the same bases. So that means I can use this property of equality, which is if I'm taking log of something which is equal to log of something else with the same base, I can set what's inside the parentheses equal to each other. So that in our case, that means I can set 4x minus 7 equal to x plus 5, and then solve for x from there. So from there I would subtract x and add 7, and I get 3x is equal to 12 divided by 3, and I get x is equal to 4. Okay, I forgot to mention this with my first example, but it is going to be important that we check our answers. So like for the first one, the check would just be figuring out what is 4 to the 1.73 power, and hopefully that's going to be approximately 11. And when I type that in the calculator, 4 to the 1.73, I do get about 11, so that checks out. So similarly, with the 4, to check my answer here in example 2, I don't actually I can just plug in 4 for x on both sides, so I get log 5 of 16 minus 7 is equal to log 5 of 4 plus 5, sorry, which is 9. So now 16 minus 7 is 9, so I have log 5 of 9 is equal to log 5 of 9. I don't even need to then plug that into my calculator. I know that's going to work out. Okay, so let's look at another example. So for our next example, we have log 4 of 5x minus 1 is equal to 3. Okay, so the idea is I'd like to find a way to get rid of this log base 4. And what I'm going to use to do that is actually going to be one of our log properties. So I'm going to actually just slide our paper down to remind us that if we take the exponent to a log power, base to a log power where that base matches, we'll just get what's inside of the log. We're going to use that property here. So the idea is I'm going to raise both sides of my equation with a base of 4. So that would look like 4 to the log 4 of 5x minus 1 power is equal to 4 to the third power. So I'm kind of going backwards in my statements of equality. If I have something equals to something, then I can raise both of those to be my exponent with the same base, right? Well, now what's going to happen on the left is that 4 to the log base 4 power, those are essentially going to cancel, and I'm going to be left with 5x minus 1. On the other side, I have 4 to the third power, which I can just calculate. 4 times 4 is 16, times another 4 is 64. So from there, I add 1, I get 5x is equal to 65, divide by 5, and I get x is equal to 13. So to check my work, I do log base 4 of 5 times 13 minus 1. I'm hoping that's going to equal to 3. We'll see. So from here, I'm going to get log base 4 of 5 times 13 is 65, minus 1 is 64. So I'm wondering, is 4 to the third power equal to 64? Yes, that checks out. Okay, let's look at one more example. So in the next example, we have log of 2x plus log of x minus 5 is equal to 2. So in this situation, I would like to eventually kind of cancel out my logs by using exponents, similar to what I was doing here. But before I do that, I need to condense the logarithms on the left so they only have one logarithm. So we're going to say condense logs first. So if I condense my logs, that means I have addition, so it should multiply. So it would be log of 2x times x minus 5 is equal to 2. And I could distribute this. So then it would be log of 2x squared minus 10x is equal to 2. Okay, so now at this point, I'd like to get rid of my log so I can then just solve for the x's inside. So the idea is, remember that this has a base of 10. If I don't see a number, it's a base 10. So in order to undo log base 10, I'm going to have to do 10 to that power. So it would be 10 to the log of 2x squared minus 10x is equal to, well, whatever I raise this side to the 10th power, I have to raise the other side to the 10th power. Now, on the left-hand side, the power of 10 and the log cancel. So I'm left with 2x squared minus 10x is equal to 100, 10 squared. Now from here, this is a quadratic equation, so I'm thinking maybe I can factor this. So it would be 2x squared minus 10x minus 100 is equal to 0. Factor out of 2. So now it's x squared minus 5x minus 50. From here, I would do the x and think, is there anything that multiplies to negative 50 and adds to negative 5? Yes. Negative 10 and positive 5. So we got x minus 10, x plus 5, set each one equal to 0. And we get x equals 10 or x equals negative 5. Now this is a situation where it's going to be important to check because especially when you get negative numbers, sometimes negative numbers don't work because we can't actually take log of a negative number. So if we plug in to check, so I'm going to first plug in 10. So we get log of 2 times 10 plus log of 10 minus 5. And I'm wondering if this is going to equal 2. So let's see. This would be log 20 plus log 5, which is log 100 if I multiply. And yes, that does equal 2. So this checks out. For the second one, if I plug in negative 5, I get log of 2 times negative 5 plus log of negative 5 minus 5 is equal to 2. And now I can tell I'm going to run into a problem because I'm getting negative values here. And the problem would be, like, if I say, if the idea here would be that 10 to what power is negative 10? Well, 10 to no power is negative 10. There's no way to get that negative number with a base of 10. So this means that this is undefined. So x equals negative 5 is not a solution. And our only solution would be x equals 10. So there are some practice problems for you guys to try, and we'll be practicing this process tomorrow in class.